This is a European eel. It's found all over Europe and it's critically endangered, with populations declining more than 95% since 1980. One of the reasons the species is so endangered is because of its complex life cycle. From birth, they are transported by oceanic currents from the Sargasso Sea to the coasts of Europe and North Africa. Here they enter freshwater, using the tides to help them swim upstream because of their poor swimming performance. After a while, they turn into elvers, about 9 centimeters long and up, and dark in colour. It is essential for them to get upstream to be able to grow large enough over a number of years to mature into silver eels and undertake a migration back downstream to the sea and back to the Sargasso. One of the reasons for the huge decline in numbers is the amount of barriers that we place in rivers that eels need to overcome to complete their migration. An example of such a barrier is a culvert. Culverts can restrict the flow and increase the flow velocity by virtue of having very smooth walls and bed compared to a natural river. The problem is that elvers have trouble swimming fast enough to get upstream of these culverts. Some fail to pass these barriers and others become overtired, so they need to rest near the culvert, where they are more vulnerable to predation. A low-cost solution to this issue is eel tiles. They simply bolt onto the bed of the culvert. They're made out of plastic and they comprise of a base and 2 densities of cylindrical protrusions. But can they help eels get upstream? And if they can, how do they do it? This has been focus of part of my PhD. They mount to the side of the channel because that is where eels prefer to swim. To simulate this, I used a flume at Cardiff University School of Engineering with the same tiles that are planned to be used in rivers, then simulated flow conditions which may occur in a river. The tiles also act to create a severe reduction in flow velocity within the protrusions, and also manage to reduce velocity above and besides the tiles. An inflection point can be noticed on the graph, level with the top of the protrusions, that shows the 2 different layers of flow. This can allow the fish to navigate the culvert much more easily in theory, but in practice things are more complicated. At the interface between the slow-moving flow within the tiles and the higher velocity flow around them is a layer of high shear. This can create an instability called the Kelvin-Helmholtz instability. This instability can manifest itself as a series of vortices which can destabilize fish. In reality, we can see that the vortices do not form in our case, but the instability causes an upward and downward shedding in the vertical plane and a side-to-side oscillation in the horizontal plane, but this can still be enough to impact a swimming fish. To better understand how the eels use the tiles, I analysed the kinematics. Without the tiles, the eels swim very fast, symmetrically, but use a lot of energy. When swimming near the tile, they take full advantage of the slower flow by tucking themselves into the slowest part of the flow and swimming asymmetrically. But when they swam above the tile, they were slow and swam with reduced amplitude, suggesting the turbulence above the tile could be affecting them. This is further supported by this graph, showing how many tailbeats per second they needed to swim in each area, essentially showing us swimming efficiency. We can see they needed more tailbeats to go faster in turbulent areas, but they still needed to swim faster in the open channel. Through all the pros and cons of the tiles, they were able to help the eels get upstream more often and more easily, which is good news, but more evidence is needed on their effect on different species and their ability to reconnect habitats. Culverts are unfortunately only one of many challenges facing eel populations. Climate change, the spread of the Aprasus parasite, chemical pollution and other barriers in rivers all threaten the species. But by solving as many of these problems as we can help prevent populations from further reducing and hopefully restore them to healthier numbers. Seemingly small devices and changes like eel tiles and other eel passes all contribute and must all work together to help do this. I would like to thank the whole team at Cardiff University and especially my supervisors, Professor Joe Cable and Dr. Catherine Wilson. I would also like to thank Andy Don and the Environment Agency for making this work possible.